I'm very happy to present here. This is the first time I give a colloquial remotely in South Africa. I'm very excited about it. I will rather start with my talk. I firstly give a brief background of the motivation of my work. The H1 and the baryonic cycle as a driver for galactic evolution. We know that the galaxies we observe in the universe, they show distinct colors and morphologies reflecting different ages, structures, and dynamic status. How galaxies evolve into these different features is a key question in astrophysics. And galaxies, they are ecosystems of gas, stars, and dark matter. And it is a baryonic flow, the cycle baryonic flow that drives the evolution of galaxies. If we start slightly far around the galaxy, around a few tens kiloparsec, we start from the circle galactic median, the warm ionized gas around the galaxy. The circumgalactic median there, it will cool and accreted onto the galaxy. It usually drop onto the outer region of a galaxy because it has high specific angular momentum. And then if there is a process that can remove the angular momentum, either the process is the bar, spiral on, or the tidal interaction, then the gas could lose angular momentum and flow inward, located onto different radius within the galaxy. And then at a certain location within the galaxy, there's a local cycle of the gas of different temperatures, different phases. The warm gas, warm ionized gas will cool to form the H1, the atomic hydrogen, neutral atomic hydrogen gas. It further cools and form the molecular, and then finally form the stars. All these processes that go before the final formation of stars, if any of them get disrupted in the way, then the star formation rate will drop and our galaxies would evolve toward the old and dynamically hot status. And so this baryonic flow, it really matters. And my focus is about one important step, intermediate step within the cycle from the warm CGM toward star formation. And that is the neutral atomic hydrogen H1 gas. Motivated by the traditional observations of the cold neutral gas, H1 molecular, we can mathematically express the process I just described in this way. The star formation rate can be expressed as a equation that starts from the global gas reservoir and then multiplied with the conversion efficiency to form the molecular, and then multiplied with the efficiency to form the stars out of the molecular. Observations in the past decades has done an extensive job to quantify each of these steps. There's examples of work by the gas and X-gas group. That is a representative sample of nearby galaxies selected by redshift and stellar mass. So it's a relatively complete sample. And based on that data, it was found that the gas H1 mass fraction, H1 mass over stellar mass, it drops as a function of the stellar mass. More massive galaxies, they are gas poorer. And then at a given stellar mass, with higher star formation rate, galaxies has higher gas fractions. So galaxies need more H1 to sustain their enhanced star formation rate. Finally, the conversion of H1 to the molecular, this efficient does not change much as a function of the star forming status. These are very nice work, and it set useful constraints for star formation, galaxy formation models. However, there was a problem. The problem is that if we take a close look at a nearby galaxy, this is the famous M83. And in the middle is this H1 map. On the right top, the velocity map. On the right bottom, the velocity dispersion map. And then on the top left, the optical image. If we plot the H1 as a control on top of the optical image, it is obvious the H1 is much more extended than the stars, than the optical light. It has different structure. And only the H1 that on directly within the stellar disks can participate directly in star forming process. All those H1 on the outskirts, they cannot be efficiently used to fuel the star formation. But you may wonder, why is this a problem? It only suggests that we need to be careful enough to always extract information about stars and gas from exactly the same locations. It is a problem because the most efficient way to survey the H1 gas mass in a statistically large sample of galaxies is by the single-dish telescopes. And this is the example galaxy at redshift 0.025. And some people may know that it's a typical redshift for SNO-selected galaxies. Actually, it's a relatively low redshift within a SNO sample. And the optical light is within this orange circle. It's a part of the H1 that directly relevant for star formation. And then the green circle is the resolution elements of the currently the largest single-dish telescope, FAST, in China. And the resolution element of Arecibo would be even larger. So basically, we don't resolve the H1 of the galaxy. To highlight the problem a bit, even with interferometry, the situation won't be significantly improved. It was predicted that over 90% of the galaxies detected in SKA precursor surveys like Wallaby, like Aperitif, they won't be well resolved. Having this problem in mind, we still really need to resolve the H1 to at least separate it into an inner part that is directly relevant for star formation and an outer part that are not so relevant. And so we revise the equation I showed before. We revise it into the equation array below. So we separate the H1 into the inner part and the outer part. We quantify the inner H1 over the total H1 as a ratio that describe the inflow efficiency. And then star formation rate is directly related to the inner H1, the immediate gas reservoir. And then we should care about the conversion efficiency of the inner H1 to molecular instead of the total H1 to the molecular. And in this work, I'm going to focus studies on these three quantities: total H1, inner H1, and the conversion of inner H1 to the molecular. Okay, let me briefly summarize my background and raise the key questions I'm trying to address during the rest part of my talk. H1 is an important part of the baryonic cycle that drives galaxy evolution. H1 can be much more extended than stars which makes it excellent tracer of the dark matter or environmental perturbations, but it adds difficulties to scientific interpretation about the star formation process. Most H1 observations in the coming 10 years won't perfectly resolve the distribution, spatial distribution in the galaxy. And the questions I'm trying to address in the rest part of this talk, including we want to firstly ask how H1 is distributed in galaxies if we have well-resolved map. Secondly, can we predict the H1 distribution based on other observables and based on the knowledge we gain from the well-resolved map? And thirdly, what can we learn from the observed and predicted H1 radial distributions? Now let's start with how H1 is distributed in galaxies. This is the sample I use. We compared a sample of H1 images from 15 projects. They all interferometric H1 maps with relatively high resolution, including over 500 nearby galaxies. And this is our key result, the size-mass relation. It was not found for the first time in my work. It was found earlier, but in this work, we compiled a larger sample, much larger sample than before, and we really extended the parameter space of the sample, both in optical luminosities and in H1 mass. And we confirmed that with so many galaxies, there is a remarkably tight relation between the H1 mass and the H1 disk diameter. And the H1 disk diameter is defined as the major axis of the 1 solar mass per pieces squared asymptote of the H1 disk. There are two key points to be pointed out with this figure. The first is that we included different types of galaxies, including the spiral galaxies, galaxies in clusters, the early type galaxies, the dwarf irregular galaxies. These different types, they lie perfectly on this relation. With a scatter of only 0.06 stacks or 14%. And secondly, if we look into the slope of the relation, it's very close to 0.5. If we move this 0.5 to the other side of the equation, it becomes 2. And then we can roughly approximate the equation like this. We get a characteristic surface density for all these galaxies at 5 solar mass per pieces squared. It implies that the H1 disks among different type of galaxies, they are very self-similar. They are very homogeneous in the surface density distributions. And if we further plot, we quantify the offsets of galaxies from the mean relation, the delta dH1, we plot it as a function of other properties of those galaxies. Now here the MH1 Vmax, B band absolute magnitude, the H1 richness, the H1 diameter over the optical diameter. We found the slope and the scatter, the offsets, it does not change at all as a function of all of these parameters. This is very surprising because here, with the very wide dynamic range, we have dwarf irregular galaxies that as low mass as our neighbor M33 and have high mass galaxies that are as massive as our Milky Way and neighbor and Andromeda. These dwarf irregular galaxies and massive galaxies, they have different star forming efficiencies. The dwarfs, they should form their stars much less efficient. these galaxies should also have different feedback mechanisms and feedback efficiencies. The dwarfs, they have lower gravitational potential. The feedback is much more efficient to push out the gas. They have different physical processes, yet these different galaxies, they maintain the same type of size-mass relation. It suggests that the physical process within the galaxy that might have an influence on the surface density of each one, they manage to obtain a sophisticated balance in order to have this very tight H1 size-mass relation. This relation, so it puts strong constraint on models of galaxy formation. So far, we could not give an exact explanation why galaxies manage to produce such a tight size-mass relation. We only know that if some recipes of the models, they go wrong, it could not reproduce this relation. For example, in an earlier version of the Eagle model, because some of the supernova feedback recipes not so correct, then for the dwarf irregular galaxies, they would produce unrealistic large holes in the H1 disk. And as a result, like this, the orange shaded region here, they would divide significantly from the observed size-mass relation. As we said, the relation indicates underlying self-similar surface density distribution. We can more directly show it like this. We obtain the median H1 radial profile for the different samples. We normalize the radius by the H1 disk size. And we can find that some of the samples, they perfectly align with each other in the outer regions. Here, the red and the pink colors, they are samples for early type galaxies. These are the different the galaxies showing different behaviors. The profiles are shallower than the other samples. They are more extended in the outer regions, of lower densities in the inner regions, implying that they have a different gas accretion or distribution history than other galaxies. But the later type galaxies, the dwarfs and the spiral galaxies, they have perfectly homogeneous profiles in the outer regions. The inner parts could be significantly different and it has much larger dispersion there, but in the outer regions, they have very small scatter. They were self-similar. We will make use of this fact later. Now we have parameterized some features about the radial distribution of gas in nearby galaxies. Now let's see how we can make use of them to predict the H1 radial distribution and statistically study their relation to star formations. We go back to the formula, and in this part, we are going to tell a story about the star formation fueling. We focus on these two parameters, MH1 in and the conversion of MH1 in to molecular. Because star formation is a process that is more closely related to the density than to the total amount of H1. So we divided the MH1 in by the related area to convert it to the averaged surface density of H1 within the stellar disks. And here's the way how we predict the MH1 for galaxies. We start from the single dish global H1 spectra. From there, we get the total H1 mass. We combined with the size-mass relation, we will obtain the H1 disk size. We combine the H1 disk size with the median H1 profile galaxies. you can see how small scatter it is in the outer region. So because the inner region has much larger scatter, we ignore the inner region at this stage. We take a radius, the R90 of the optical radius. It could also be R25. Basically, it's a radius that characterize relatively characterize the edge of the optical disc. Because the outer parts, the scatter is so small, we can relatively reliably predict the H1 mass in the outer regions. Then we subtract it from the total H1 mass, we obtain the MH1 in. So that's how we obtain the H1 amount in the inner disk. And we also quantify the reliability of this method. The scatter between the predicted and the real MH1 is relatively small. It's 0.09 dex. If we compare the predicted and the real H1 average the surface density, and the scatter is also relatively small, 0.6 solar mass per pieces squared. We applied to the gas sample. We remember that the homogeneous profile in the outer region only applies to late type galaxies. So here we selected the disk dominated galaxies to apply our method. We will make use of delta star formation rate, delta central surface density diagram. What is this diagram? In the local universe, actually generally for galaxies, for star forming galaxies, there is a relation between the star formation rate and the stellar mass. That is called the star forming main sequence. We can measure the distance of galaxies from the mean sequence. So that delta star formation rate is a measurement for star formation rate enhancement. If it is negative, it is a measurement for star formation rate suppression, right? And also for the disk-dominated galaxies, there is a relation between the central surface density and the stellar mass. We can also measure the distance of galaxies from that mean relation, the delta central surface density. And it measures how compact the galaxy is in the central parts. And it is known that in the delta star formation rate, delta central surface density diagram, galaxies are distributed in an L shape or elbow shape. And then the star forming galaxies, which has delta star formation rate around 0, they can have a wide range of delta central surface density. But for the galaxies deviating from the star forming main sequence, those quenched galaxies, they are in this part of the L shape. In other words, to put it in a simpler way, it implies that galaxies needs to have a compact center in order to get quenched. Here, because we selected the disk-dominated galaxies, we missed the quenched part of the L shape. But let's see what can we learn from this part of the L shape. Here we color-coded the disk-dominated galaxies with these 3 new parameters we derived with our method. The averaged H1 surface density within the stellar disk, the conversion efficiency of inner H1 to molecular, and finally, the total cold gas, that's a molecular plus MH1 in over the star formation rate. It's a measure of gas depletion time. It is also called gas depletion time. And we can find clear trends in all these 3 panels. It both goes from the direction from the left bottom to the top right, that the most compact And most star-forming galaxies, they have the highest averaged H1 surface density. They have the highest efficiency of converting the H1 to the molecular. And they have the shortest depletion time. What does it indicate? These trends, they are perfectly consistent with the theoretical compaction model for galaxy evolution. The compaction model predicts that the galaxies, when they start forming, they evolve fluctuating around the star forming main sequence. If we take a galaxy that starts from very close to the star forming main sequence, initially it does not have very high star formation rate. So the gas that fills the star formation rate will continuously flow in and then pile up in the center. So the galaxy will, the gas will compact, goes through this compaction in the center. With the gas density go up in the center, the star formation rate would also go up. The star forming efficiency would go up as well, because the Kenney-Kahler-Schmidt law is superlinear, right? All these quantities, they continuously goes up until at a point that is the peak of compaction. The star forming efficiency is so high, star formation so vigorous, then the gas quickly, violently depleted in a very short time due to the quick absorption and due to strong feedback. And then the galaxies quickly drop onto the bottom envelope of the star forming main sequence. Now, with very little gas, the star formation rate has dropped to the relatively low value there. It does not have the capability of push away the gas anymore. So if with further replenishment of the cold gas with low gas equation, then we can restart the process again. The gas come in and accumulate in the center. It will go another round of compaction, reach the peak, and then go another round of the depletion. It will fluctuate like this until at a point, if there's no more gas accretion, possibly because the halo of the galaxy already become very massive, the temperature, virial temperature is very high, the circle galactic medium could not efficiently cool anymore, then the galaxies will successfully quench, drop away from the star forming main sequence. That's the story of the compaction model. And our trend, we remember these galaxies, they have the highest density, highest efficiency, converting to molecular, the shortest depletion time. It is exactly consistent with the peak of the compaction model. Is a strong support for this compaction model. This compaction model theoretically was proposed to explain the formation of blue nudges at high redshift, to explain the conversion of the blue nudges to the red nudges. But our observational results suggest in the low redshift universe, it may still happening, although to a much gentler, much milder, in a much milder way. So that's a part of the star formation fueling story. Now let me tell another story about another part of the baryonic cycle of the gas. We're going to talk about room pressure stripping. We are going to focus about this part of the baryonic cycle. It is a global gas reservoir. If it drops, it will also affect the final star formation process. And environmental effects is an efficient way to reduce the total H1 mass in galaxies, particularly for low mass galaxies. And room pressure is one of the strong environmental effects. Run pressure is a process that happens when galaxies through clusters. Its interstellar medium will interact with the intercluster medium, and because of the transfer of the momentum, the interstellar medium of the galaxy will be pushed away in the direction that is opposite to the inflow direction of the galaxy. For example, here the two images, they show two example galaxies in the Virgo cluster. And for this galaxy, the inflow direction is this way, gas is stripped that way. For this galaxy, inflow direction is this way, again, the gas is stripped in the opposite way, opposite direction. Theories predicted that run pressure stripping is an efficient way to reduce the total H1 mass. But run pressure stripping is only directly observed for a few individual nearby galaxies. But now with the Jellyfish project, the number has raised to over 100, but still that's for individually sampled galaxies in clusters. So statistical importance of the effect was only observationally supported in an indirect way, while the significant drop of total star formation rate or total H1 mass near the core of the clusters. When I say the statistical importance, I mean when galaxies inflow into clusters, particularly for those gas-rich ones, how large the fraction of them has been affected by run pressure stripping. We try to more directly quantify that fraction in this work. This is a simple model, the Gang and Gott model. I should put a reference there, sorry. Anyway, the run pressure from the intercluster medium is described by this equation. It's the intracluster median density multiplied by square of the velocity of the galaxy travels through the cluster. And the run pressure can successfully remove the gas from the galaxy if it exceeds the anchor force of the galaxy's gravity to return the interstellar medium. The anchor force from the galaxy gravity can be described by this equation. It depends on the gravitational surface density and the surface density of the gas. So we can consider two characteristic radius here. These surface densities, therefore, they're not the average surface density within a circle. They are the surface density at a particular radius, at a certain radius. We studied two characteristic radius here. One is the optical R25. The other is H1 radius. By definition, the H1 radius is related to a H1 surface density of 1 solar mass per pc squared, right? But now we need to know the H1 surface density at R25. We will talk about that later. And we divide the galaxies into strong run pressure, weak run pressure, no run pressure. We call it a strong run pressure if the run pressure exceeds the anchor force at R25. It means that the run pressure can remove the gas very close within the stellar disk. We call it a weak run pressure case if the run pressure does not exceed the anchor force at R25, but it exceeds the anchor force at RH1. It means that it can strip the gas beyond the stellar disk. And finally, we call it a no run pressure stripping case if the run pressure is lower than the anchor force at RH1. There's a way how we predict the H1 surface density at R25. It's similar to, but slightly different to the method we showed before. We still started from the total H1 mass. We combine it with the size-mass relation to predict the H1 disk size. We combine the disk size with the median H1 profile to predict the H1 radial distribution. And then we put R25 on it to interpolate for the H1 surface density at R25. And here's a figure tested with Viva sample galaxies selected from the Virgo cluster. The cyan circles showing that our method worked okay. It predicted the H1 surface density at R25 with an accuracy of around 0.16 dex. And here's our key result. We quantify the fraction of infalling gas-rich galaxies suffering from run pressure at a different cluster-centric radius. And we found that out to twice the R200, that's a measure of the virial radius of the cluster, out to twice the virial radius of the cluster, around 50%, 40 to 50% of the galaxies suffering from a strong or weak run pressure stripping. That's a significant fraction of the infalling gas-rich population. And because the cluster-centric distance extends to twice the virial radius, galaxies can travel long distance, travel long time before it reaches the core of clusters. So the weak run pressure stripping could accumulate. It has the time to accumulate to significant effect. It potentially has that effect. Let's better understand these 2 points by comparing with simulation predictions. Firstly, the fraction. Actually, the illustrator G recently exactly provided a estimation of the ratio of galaxies, gas-rich galaxies suffering from run pressure stripping. And the ratio it gives is around 30 to 60%, considering the projection effects. It's very consistent with the fraction we obtained. And this is the fraction. And then whether these weak run pressure stripping should, whether the effects are significant, whether should we care about them. And the simulations suggested that indeed, at the time when the run pressure reaches a stellar edge in the simulation, the amount of the effective run pressure stripping accounts for around 40% of the final stripping. So the effect is indeed, at least it cannot be ignored. So basically, our observational result is consistent with simulation, and combined with simulation, it suggests that a significant fraction of the infalling gas-rich galaxies suffering from run pressure stripping, and it starts from well beyond the virial radius, and it could potentially have significant effect. The significant effect is both from the stripping of the H1 and also from the consumption of enhanced star formation. The enhanced star formation is a consequence that the pressure, it increased the internal pressure of the interstellar media and increased the star forming efficiency. Why is this result important for galaxy evolution? In previous studies, it was quantified that galaxies infalling into clusters, they experience 2 stages of star formation suppression, a slow quenching phase and then a fast quenching phase. The fast quenching phase was undoubtedly attributed to run pressure stripping, the strong run pressure stripping close to the cores of clusters. However, the slow quenching phase was explained as a consequence of strangulation in most earlier studies. Strangulation is a mechanism that also results from room pressure stripping, but not stripping on the cold gas, but stripping on the circumgalactic medium, the hot gas around the galaxies. And our result now suggests that the room pressure could have an effect on the cold gas from in the slow quenching phase. And slow quenching phase is not totally due to strangulation. And another thing is that it was found that be at the edge of the clusters beyond the virial radius, the infalling galaxies, they already have lower star formation rate compared to filled galaxies. This phenomenon was termed pre-processing. It says that the galaxies, they were already processed, the star formation and gas amount already reduced before they are processed by the cluster environment. That was a past things. And it was, and the pre-processing were mostly attributed to environmental effects within smaller groups that inflow into the clusters. But now our result suggests that the room pressure stripping of the cluster itself, it could start far beyond the virial radius. So the pre-processing need not to be totally attributed to the group environment. It could actually be processed by the cluster itself through the weak room pressure. So now I have given two stories about the baryonic cycle of galaxies, about the different influence of the H1 and H1 on star formation. Here's a summary of my talk. We found that the H1 size mass relation is remarkably tight, and it is there's no difference in dwarf or massive galaxies. The relation is linked to a fact the dwarf and spiral galaxies have a homogeneous radial profile of H1 surface density in the outer regions when the radius is normalized by the H1 radius. And we use these facts to predict the H1 surface densities based on single-dish measurements. And with the predicted H1 radial distributions, we found that the filling of the inner H1 is an important part, is an important quantification to understand the filling of star formation in galaxies. And also with the predicted H1 radial distributions, we found that a significant number of infalling H1-rich galaxies in massive clusters suffering from room pressure stripping far before they reach the core region of clusters. That's my talk. Now I'm ready for to take questions. Thank you.
Okay, so I'm sorry I could only join the second half of the talk, but I would like to ask you, how do you define this RH1? How is it defined for a galaxy?
It is defined as the semi-major axis of the azimuth at a level of 1 solar mass per pieces squared.
Okay, so you found an universal relation for the profile, which is independent of the mass of the galaxy.
Yeah.
For the profile, I mean. Okay. I'm sorry, I could only join the second half due to time being, but okay, yeah. Okay.
And here, the reddish colors are for early type galaxies. They have different profile shapes, much shallower shapes. But for the other samples, they are for the dwarf irregular and spiral galaxies. They have perfectly homogeneous profile shape. And here's another way to express it. If we directly plot the median profile scatter in the outer region, it looks like this. In the inner region, it looks like this.
Okay, and did you try any analytical fitting relation for this profile? Some analytical model?
Yes, because the inner region, it has large scatter, so we can focus on the outer region, and there the scale length of the disk, if we model it with the exponential disk, the scale length over H1 is around 0.2.
Okay, so it's exponential decaying for the surface density. Okay.
Yeah.
Okay, thank you.
You're welcome. Thank you for your question.
Yeah, so I have two questions, and other than that, I want to chat with Dr. Wang just after this for some other research-related questions. So one thing is that when you show this, there's a very interesting plot showing the size between the H1 of the galaxy and also the optical part, and there is a symbol called R25. Is that something related to the very central part, like the optical image of the stellar disk or something? R25. Interesting. Yes, this one, yes. Yes. Can you see my, is this just means optical? Can you see my my pencil? Yeah. This means just the optical image. What does that 25 represent to?
It is optical. It's defined as a 25 magnitude per arcsecond asymptote semi-major axis. Usually it is defined by the B band, but here we use the G band, which is very close to the B band.
Okay, I see. And you can, okay, from there you show the H1 is much more extended than optical part. Okay, I see. And the other thing is just very basic question. How do you measure the H1 mass through your interferometric technique? Like, I mean, for instance, you mentioned all of this, which are very crucial. And how do you get it? I mean, interferometric would give you visibilities, right? And then how do you convert that into the H1 mass?
Yeah. The interferometry first need only involves in the first part of method, and within the interferometry we obtain the visibilities, and we use the softwares to convert it to map it onto the regular coordinates, pixel coordinates, and then we need to do the deconvolution to clean the map. But these steps, they mostly the major purpose of them is to map them onto regular pixels and to change their dirty beams into a clean beam so that we have more regular shapes of the galaxies. Otherwise, for a point source, we would have satellites, rings around a bright central point. These processes, so they are mostly to better reveal the shape of galaxies when the galaxies are resolved. But to convert that to the H1 mass, it is actually the same for interferometry and for single dish. Basically, it's a 21 centimeter emission line. And if we ignore the self-absorption, we assume an optically thin disk, then we can directly convert the luminosity to the number of atomics, hydrogen atomics, and convert it into the mass. In my work, all the disks are assumed to be optically thin for simplicity, but now it is more and more realized that for edge-on galaxies, it's better to correct for self-absorption. So there are equations, there are empirical equations that are based on the inclination of the galaxy to provide a correction factor to account for the self-absorption.
Okay, I see. Just to a very crude, route. Basically, you got visibility Vij from all of your interferometric like these arrays, and then you somehow converted that into image, and then you do the dirty beam to primary beam corrections, right? There's a correction and let's say beam corrections. Okay, and then you will get the cleaned image. And then somehow I mean, this is the link which I don't understand. Once you got this image, how do you get MH1 after this? what is this process in between?
When we get the image, basically we get the 21 centimeter luminosities. Before this, what we obtain is actually a data cube, right? On the data cube is a many channel of images. Each channel represents a velocity slice, or in another word, the frequency slice. But then if we select a position on the sky, we go through the different channels. That's a H1 spectrum for that sky position. So we can do projections to collapse all the channels to project them onto the moment zero, which is which for each pixel is a luminosity of the spectrum on that line of sight through different channels, through different velocities. So we get the luminosity, get the flux for each sky position, and combining with distance, we get the luminosity. We add the luminosity we obtain on different positions on the galaxy. We get the total luminosity, the cumulative total luminosity of the galaxy, and then we convert that into the H1 mass.
Okay, yeah, some step involved. Yeah, I'm quite new for that process. Yeah, okay, I see. Yeah, I may need to look in more detail for that. But that's all my questions for now. Yeah.
Okay.
Later, I will chat with Dr. Wang with others. Yeah.
Yeah, I think Matt has a quick question. So
I have a question, but it's not a very well thought out one. So just going back to your plot of, you've got like size versus H1 mass for the galaxies. So this is going out quite to large distances into the galaxy halos, is it?
Yes, for some of the galaxies, as you see, over 100 kpc.
Yeah, okay. So I was just wondering, so this is why it's not a very well thought out question, but so these are all spiral galaxies. Our galaxies all have like dark matter halos. Does this tell us anything about the dark matter halo properties across all the different galaxies? And like, you know, how this works, the Tully-Fisher relation, all that kind of stuff.
Yes. Yeah, because these H1 disks, they are so extended and they are relatively dynamically cool. They're rotational dominated, so they're excellent tracers of the dark matter halo. Actually, the earlier days, the first probes of dark matter halo is via the rotation curve of H1. Because if there's no dark matter halo, if there are only the bright baryons, then the rotation curve should drop beyond the optical edge of the galaxies. But in fact, the rotation curve traced by H1 were found to be flat, reflecting that there is a mass there that are invisible. That the earlier days, how the dark matter were firstly noticed. Today, the H1 is still considered one of the most reliable way to obtain the dark matter mass for individual galaxies. And basically, one can assume a dark matter distribution model as a isothermal model or an FW model. Then one can measure the gas mass, the gas or the atomic gas, the molecular gas, and also the star mass. One subtract the contribution of this baryonic mass from the rotation curve, then one can model the dark matter mass distributions. Is that your question?
Yeah, like I said, I'm not sure this is a terribly well thought out question. I'm just kind of wondering if yeah, do you need to do anything? You don't need to do anything. You don't need to worry about dark matter at all and what the distribution is in the different galaxies across this range in mass. You don't have to worry about how that varies or anything, or if it does vary, or it's just not relevant. I'm just, yeah. Like I said, this is not a well thought out question.
I would say, who knows? Currently, most of studies, it only focuses on how dark matter affected the distribution of the gas. It put the gas on such rotation velocities, but most studies didn't think whether dark matter affected the size-mass relation, because from the first impression one would have about the gas densities, one would think the processes, the more energetic processes like the feedback, star formation, the inflow, the external perturbation, they should leave stronger imprints on these gas distributions. The dark matter, it's like an underlying gravitational potential. It just determines at a given radius what velocity, what rotation and dispersion, what type of kinematic feature the baryonic matter should have in order to stay there in a relatively equilibrium way. That's usually how this problem was attacked. Yeah. So basically, there are not much studies about how dark matter affect the size-mass relation.
Okay, thanks.
Thanks a lot. I guess we are almost, it's over the time. So thanks a lot for giving this talk, and thanks everyone for joining in.